Hello, flat earth researchers, debaters and debunkers. Let's have a look at this curvature measurement challenge that was an idea put forward by Leon, one of Phuket Word's Patreons. And thanks to the Patreons for helping get this spangling new whiteboard, a little bit larger than the one I've been using before, but not quite big enough. It's the biggest one I could find. But a good chance to put forward one of these old school presentations. So here we're going to talk about measuring curvature and whether it is at all possible. So far, believe it or not, no one has ever measured any curvature on the surface of the Earth in more than 500 years of so-called scientific discovery by the heliocentrists. Everything we assume about curvature on the Earth is done by taking other aspects of what we see going on in the sky and then converting that into this curved surface, which is, I believe, to be imaginary. And in reality, what we have is a level surface. But if you wanted to come along and argue with someone like myself, who looks at what we experience in reality as being on a level Earth, then what you have to do is come up with an actual tangible, repeatable measurement of the curvature on the surface of the Earth. And so let's have a look at how we could do this. What I've got here is I've set up this scenario where we're going from Portsmouth in the UK over here on the left to New York over here on the right, or on this curved surface from Portsmouth here to New York on the right. So, you know, we'll just look at two. But what we've got to do here really is see if we can actually measure a difference between level and curved, because it's fairly simple enough to imagine it, or say, well, the level surface that we experience is curved because we've converted it into degrees, but that's never been measured. So all we have is explanations and extrapolations from other things that we see, rather than an actual measurement. So, you know, after this, your recommendations and comments are welcome. How could we actually go about doing this? What kind of tools could we use? So what we have is this distance between the UK, the port in UK, Portsmouth in UK, and New York, which is 3,632 nautical miles. Let me just put the N back here, nautical miles, and this is supposed to be degrees, which turns out to be 60.5 degrees. Okay, so you can refer to this distance as 3,632 nautical miles, or you could just say it's 60.5 degrees, and it's the same. Because you may or may not know that 60 nautical miles is equal to 1 degree, and that's why nautical miles is used instead of miles or kilometers. The nautical mile was invented, I suppose, as a way to represent distance in terms of degrees. So what we actually have here is, if you take this 60 nautical miles per 1 degree, then you take that distance, 3,632 nautical miles, divide it by 60, because of this, then we actually get 60.5 degrees of curvature. Okay, so there's basically should be a difference of 60.5 degrees of curvature from the vertical axis to the next vertical axis in New York, that amounts to this. Okay, so that's what we've got from if you want to represent it as part of a circle. So let me just preface this by talking about a ruler. All right, so you've got a nice long ruler here, and we can even mark off 60 on here. Let me just get rid of the pens. Okay, 60 is there where my finger is, and there's 0. So we have this distance here of 60 units, and in this case, of course, it's centimeters, but we can say that it's nautical miles. All right, and it's level. So if we do this and we curve it, and this line, this distance, becomes part of a circle, then the distance doesn't change, but then we can create an imaginary point for this circle, and then we have a radius, and then that gives us this ratio of 60 nautical miles per 1 degree. But the distance doesn't actually change, whether you consider it to be level or convex or even concave. Yeah, the distance would not change. So people talking about distances means absolutely nothing, because again, it all depends on how you envisage it. All right. And we could also talk about, for example, a thermometer. That's a good example, because actually a thermometer is a scale of 0 to 100. Sorry. Okay. All right. There's 100 degrees. Okay. There's 0 degrees. All right. There's 50. Okay. We'll just. Oh. All right. So you've got these 100 degrees between freezing and boiling, all right, on the thermometer. Okay, that line can be as long as you like, but I suppose it just depends on the capillary action and the volume of the thermometer that you're using. But essentially, we're already talking in terms of degrees. These units of measurement, they've been made up by man. We've divided this temperature difference between 0 and 100 degrees into these units, that or 100 units. All right, so these units are called degrees, but they're degrees of temperature. So it just goes to show that you can you could represent this as part of a circle. You could say this is 100 degrees. Yeah, it's not a full circle, 360 degrees, but you could imagine it as being part of a circle. Yeah, and you'd end up with a segment like that to represent something that is in no way related to a circle, but it's just a way of projecting the information, or that scale of distance that we have on a thermometer between freezing and boiling. Yeah, so that's that should help clarify that just because we're using degrees when we're talking about distance across the Earth, it doesn't mean that the Earth is curved. It just means that we can take the distance that we've measured or calculated and turn it into a number of degrees and create this piece or section of what would be a circle if we continued it and we carried on using degrees as our measurements until we got to 360 degrees. It doesn't mean that going from Portsmouth to New York and then continuing on will actually bring you back round to Portsmouth. What it means is that you can just represent Portsmouth to New York as part of an imaginary circle, and then that part is equal to 60.5 degrees in our particular scenario. Yeah? Okay, so the calculations are easy enough to make, all right? And as we know, the radius that is assumed to be from the surface of the Earth, of the globe Earth, to the center of the globe Earth is 3,440 nautical miles. Now, of course, again, no one actually took a ruler and measured that distance, did they? No one did this. No one's gone down and measured where the center of the globe Earth is. They've simply taken a radius that's similar to the distance from the North Pole to the equator, and because of that you can then kind of just do that 4 times and you've got this circle. Again, it's just a representation of something that isn't a circle at all, but you can just turn it into one. So with the 3,440 degrees, nautical miles, you do this pi mathematics, and that will give you the circumference. And as you know, you can put this equation around any way you like, or you could you might not have this number, but you can make the number by just filling it in until you get the answer that you desire. All right, so as you know, if you're going to do the circumference of a circle, then you just do 2 times the radius. Okay, so plug in 3,440 nautical miles, multiply that by pi, and that will give you the circumference. a full circle that is equal to 360 degrees. And that turns out to be about 21,600 nautical miles circumference. So that would be pole to pole to pole, or it would be around the equator. Same thing, isn't it? Because we're talking about multiple lines that have been turned into a sphere. And those lines are just divided by 15 degrees. And 15 degrees is based on time, because we're talking about 24 hours, and you end up with 15 degrees per hour. Doesn't mean that the Earth is turning at 15 degrees per hour. It just means that there's a distance that has been equated into degrees between two locations that are that distance apart, 15 degrees apart. Yeah, and that's time. That's representing time. So again, because we use degrees, really, we use circles to represent time. If we turn the distances in nautical miles into degrees as well, we can then operate on this same circular mechanism or methodology for putting together a model. So the globe model is just that. It's just distances converted into degrees, and also matched with time, which is also represented in degrees, and direction, which is also represented in degrees. And so that culminates in a sphere. All right? So fine, we can do the mathematics to calculate what a spherical Earth would look like, or a projection of Earth and locations and different directions can all be projected onto a globe. It doesn't start with a globe, it starts with a level Earth, and it starts with measurements and converting them into degrees. But we're talking about how we measure. How do you measure the difference between a level surface, which is what we experience, and a circular surface? Because you know, you would go along here, for example, starting off in the UK, and let me just use a different colour for this. We can use green, okay. And so we would have our plumb line, wouldn't we? And we would have our horizontal. That would give us 90 degrees. But anywhere along the surface, so even halfway, you'd still have a vertical plumb of 90 degrees and a horizontal of 0 degrees all the way. Nothing would change about what you're doing, okay? So the globe Earth proponent will say, oh, well, gravity is just creating your down in this direction, and level is curved because you're staying at the same distance from the center of the imaginary circle, and so you carry on going like that, and that's the same as level. But what I'm asking, what the challenge is and should be for anyone claiming the Earth to be curved instead of the level Earth that we experience, is to say, okay, this is how you measure the difference between level and curved. There is a difference, right? There is a tangible physical difference between these two types of surfaces. If you can say that, one is the same as the other, but that's not science. That's pseudoscience. That's just changing one to fit a different model based on, you know, the heliocentric model. I'm asking for anyone who has the capabilities or the tools or the imagination or the will even to see how they can measure the difference. So what is proposed here is really quite simple. You start off in Portsmouth with your plumb going down here and your 90 degrees. Okay, that's normal, just as we have it there. But as you go along the journey, we keep this plumb fixed. We keep it in some kind of memory bank or marked somehow, and then as we travel along the surface, what we should then see is a difference between the original plumb and the current plumb when we take our next measurement. So let's say this is about halfway. So we should end up with a difference here between the green one. The green line here represents this original plumb here, okay, and then we've got a new plumb here with this down direction, allegedly, on the outside of a spherical Earth. And so there's a difference here. Should be about 30 degrees difference between the original plumb and the current plumb. Now, of course, that's easily calculable. You could say, oh, I've traveled this much distance, and so the difference is that, okay? But how are you going to measure it? How are you going to prove that you had this tangible physical pull, if you like, of gravity down towards in this direction, and then as you moved across the surface, that then that down then moved into this direction. Totally understood that as shown here, you could say nothing changes. Well, it doesn't, but how could you measure this alleged change? So you've got a, you'll have about a 30-degree difference here, and by the time you get over here towards New York, it's going to be more like a 60-degree difference between your plumb and the old plumb, from the departure point. So you're going to end up with 90 plus 60 here, and you're going to end up with 90 plus 30 here. Yeah. How can this be done? That's the challenge. Yeah. Explanations mean nothing. Assumptions mean nothing, because it's understood that this is just an assumption and a conversion of a distance into degrees. Okay, we've done that. Now show us how you actually arrive at that with a physical, tangible, repeatable scientific measurement. Okay? Looking forward to hearing some ideas on how this could be done, and why it hasn't been done in all this time after people started claiming we lived on a globe. Because other planets are spherical, aren't they? And because you couldn't see Polaris if you went beyond the equator on a globe, blah blah blah. Yeah, that's just all explanations to fit a concept. Show us proof of concept with measurements of the difference in the degrees of down on any given voyage. All right, looking forward to it. Thank you very much.